Okay, couple of reminders for tomorrow. Okay, you may start a little bit early, so let's say.
Pardon the interruption.
Okay, so tomorrow you can start at 12:05. Come in here at 12:05 if you want to get the extra 15 minutes of writing time, but then at the end of period 3, the test is over. Okay, so make sure that you're ready for that. And all you need to bring with you is your calculator and whatever you're going to write with. Formulas are on the front, same as they have been on every other test. Okay, and phones will obviously have to go in the pockets over there. Okay, that means Thursday we're going to go over the test and continue on with Unit 4. So, Unit 4 has to do with two things. Simple harmonic motion, that's kind of the first third to half, okay, and waves, that's the second half, all right? So the reason we do simple harmonic motion first is because simple harmonic motion is usually what produces waves, so it makes sense to do that first. All right, so we're going to be going over what simple harmonic motion is, okay, how it can happen and be maintained, and we're going to look at two common examples of simple harmonic motion. That would be a mass oscillating on a spring, okay, or a pendulum. There. Almost lost my double duty demo here. Okay, so formerly the circular motion demo is now the pendulum. Taxpayers are getting their money's worth here. This costs them nothing and it does two things. Okay, so pendulum swings back and forth, right? What makes it do that?
Inertia? Or like momentum,
I mean, momentum, I guess it's involved, but like, in order to get the pendulum going, I just pull it out to here and let it go. Agreed? What makes it keep moving back and forth after that?
Gravity.
Gravity, yeah. Right? Is it constantly turning one form of energy into another as it swings back and forth? Right? Gravitational potential into kinetic. Okay? If this was a perfect pendulum, once I pull it out to the side and let it go, would it go forever? Absolutely it would. Okay? So the thing that keeps it going is gravity. But gravity is constantly fighting itself as this thing oscillates. Would you agree? Right? As I pull it away, gravity wants to pull it back to what we would call its equilibrium position. That's where it would sit if it wasn't disturbed. Okay? I disturb it by moving it away to the side. Right? Once I let it go, gravity pulls it back to the equilibrium position. Problem. Once it gets there, it's really moving. And it's going to go right through that equilibrium position and go to the other side. Now gravity's fighting itself. Okay, it gave it all this kinetic energy, now it's got to slow it down and try and bring it back to equilibrium. All simple harmonic motion works like that. There's an equilibrium position that is never achieved for more than an instant because there's a force that keeps working against itself. Okay, everyone with me so far? So there's always something working to bring the oscillating object back to equilibrium. But by the time it gets there, it's moving too fast and it just goes right through, swings off to the other side. For the pendulum, that force is gravity. What would it be if I'm talking about a mass on a spring? If I wanted to get a mass on a spring going, what would I have to do to the spring? Pull it or push it. Yeah, if I either have to stretch it or compress it. Do I do work in both of those situations?
Yeah.
So I give it energy, right? Elastic potential energy, but I give it energy. Once I let it go, the spring pushes it back to the equilibrium position. But by the time it gets there, it's got too much speed. It goes right through. Then I'm starting to stretch the spring after that. The spring is pulling it back to equilibrium. Pulls it back, okay, goes through, compresses the spring. Spring tries to push it back to equilibrium again. And it just keeps oscillating back and forth. Okay, and the motion is basically identical over and over and over again. Okay, everybody all right with that idea? Okay, think back to Science 10. You did that lab where you pulled the rubber band with the spring scale? If you were in my class, you should be nodding your head. I still remember doing that, Mr. Cougar. It was cool. It wasn't cool, but we did it. Okay, so we pulled on the rubber band. Okay, when we pulled on the rubber band, we put elastic potential energy in the rubber band. Agreed? Okay. As we pulled, did the force increase linearly? Like if I pulled it 1 centimeter and it took 2 newtons, how many newtons would it take to go forward? 4 times as much? Okay, like it's always linear. The further I compress or stretch a spring, it will linearly pull harder to get back. That's crucial for simple harmonic motion to happen. If the force becomes exponential and you get all these weird energies, okay, contributing to it, and it doesn't end up working right. Okay, so for simple harmonic motion to work, the force that's trying to push or pull the object back to equilibrium has to get bigger linearly the further away from equilibrium it gets. Okay, with a spring, that's fairly obvious. The more I push the spring, the harder I have to push the spring. Agreed? Does gravity change? Does the force of gravity increase the further away from equilibrium I get on this roll of tape? Like the weight of this roll of tape is the weight of this roll of tape. It doesn't change whether it's here or here, does it? Okay, so how can a pendulum be an example of simple harmonic motion if the force pulling it isn't going to increase? Which way does gravity pull? Which way is this thing moving? Is this moving up and down? It's moving in an arc. Would you agree? Okay, so that's how we get the linear increase. If I have a pendulum, okay, and it's swinging like this through an arc, okay, when it gets, if it got way out to here, okay, gravity would pull it straight down. Agreed? But it moves through an arc. So gravity is always going to pull straight down, but that's not the way the pendulum goes. The pendulum goes along the arc. The further from equilibrium I get, the longer that line gets that acts along the arc. So the force of gravity may not increase, but its component along the arc does. Okay? Everyone okay with that idea? Right? Like if I just pull the pendulum out this far, is there very much force trying to pull it back? If I pull it out this far, is there a lot more? Yeah. Okay? Because it's along the arc. Here, gravity is, straight down. It's right along the arc. But here, gravity is straight down, but its component along the arc is smaller. And that's true the closer to equilibrium I get. Okay? Everyone all right with that idea? And just so you know, because sometimes people really have trouble with the idea that the force increases linearly away, but the force of gravity doesn't increase. You're right. The force of gravity doesn't increase, but the part of it acting along the path does. Okay. All right, so playground swing oscillates back and forth. The playground swing is just a pendulum. Okay. You have a vibrating guitar string. That's also an example of simple harmonic motion. Okay. That's how we can use strings to make music. If I pluck a string, it's going to make a certain sound. Okay, because it's going to oscillate back and forth at a certain frequency or with a certain period. Right? Different strings will oscillate at different frequencies because the strings are all what? They're all what? Different sizes, yeah. Okay? Some of the strings are very thin, some of them are a lot thicker. Okay? That means that some of them have more restoring force than others. Okay? If they're thicker, they have a greater, what we call a spring constant. They want to go back to the equilibrium position quicker, so they all oscillate at different frequencies. And of course, you can make a string oscillate differently by just pinching it against the, what do you call the thing you hold on to? I don't know instruments. You're playing a string, isn't the what? Fret, that's the word I was looking for. Okay, the thing you pinch the string against. Okay, if you pinch it in a different place, do you make a different sound? Okay, because you change how long the string is. Okay, and pinch it against anything past your finger can't vibrate anymore. Right? So all of those things are vibrating with simple harmonic motion. They're just oscillating back and forth along the same path because there's something trying to pull them back to equilibrium. For a guitar string, it's the elastic nature of the string. Okay? For a pendulum, it's the component of gravity along the arc. For a mass on a spring, like this thing in the middle, going back and forth, it's just the spring itself. Okay? The spring tries to push it or pull it back to equilibrium. Okay? For every type of simple harmonic motion, there is what we call a restoring force. Okay? So, it's not even, the word's not even on here. So it's called restoring force. I think it's on the next slide. Okay? There has to be a force trying to restore equilibrium. That is, bring the object back to equilibrium. Okay, so all of those examples on the previous screen, okay, had an equilibrium position. For a guitar string, it's simply the resting position of the guitar string, straight up and down. Right? For a playground swing, it's the middle. Okay, and for a mass on a spring, okay, this would be, if we're looking at this as a mass on the spring here, the green dotted line is the equilibrium position of the mass. It's where it would sit if you didn't bother it. Okay? As soon as you push it in one direction or the other, okay, then it starts to oscillate back and forth, but that position will always be in the middle. Okay? Everybody with me there? All right. So if I push the mass this way, which way does the spring push? The other way. Yeah, spring always pushes opposite. So if I compress the spring to the left, the spring pushes to the right. Is that back to equilibrium? So I let that thing go, it's moving back to equilibrium. The spring is the restoring force in this case. Okay? If I pull the pendulum away, the component of gravity along the arc is pulling it back to equilibrium. Okay? There's always got to be this force trying to restore equilibrium for simple harmonic motion to occur. If that's not there, then there's no reason for it to go back to equilibrium. All right, so for simple harmonic motion to occur, true simple harmonic motion, okay, the restoring force has to vary linearly with displacement. And that displacement is measured from equilibrium. So the further from equilibrium you get, okay, the harder that restoring force pushes or pulls. You got that, friend? Do you want to go release them into the wild? Yeah, go ahead. Okay, everyone all right with that idea? That's probably something that could be a multiple choice question in January on your Unit 4 exam. By the way, this stuff is not on tomorrow's test, just in case there was any confusion. Okay, thinking of something else. Okay, so a couple of the things that we talked about in Unit 3, period and frequency, play a role in simple harmonic motion. Okay? After all, we do have something following the same path. It may not be in orbit now, but it's following the same path. The time it takes for it to make one complete cycle is the period. The number of cycles per second is the frequency. Okay, so those terms are still going to be the same. A couple of new terms, okay, that are going to come in are things like amplitude. Okay. So amplitude is how far, the maximum distance from equilibrium that the oscillating object would move. Okay. Anybody in here got a big stereo in their car? One in your room? Do you have an amplifier?
Yeah, I got 3 of them.
3 of them? Okay. What does an amplifier do? Okay. And what does it make the speakers do?
Vibrate.
When you turn it to 11, because I'm assuming yours goes to 11, okay, what happens to the distance the speaker moves?
It increases.
It increases. An amplifier increases the amplitude of the movement. Okay? If you've got your amp on and it's just, a little bit on, your speaker's hardly moving at all. okay? But if you're like the guy that drives by my house all the time, you know, that guy, okay, that, you know, makes the house vibrate when he drives by, okay? His subwoofers are probably going like this, okay? They're moving a lot because he's creating a sound with a very large amplitude, okay? His amplifiers are making that distance greater, okay? The greater the distance they move, the more energy they are going to have. Okay, does that sort of make sense? Okay, so amplitude, okay, just make sure you know the definition of that. That's the maximum distance that an object would go from equilibrium. So if we're looking at a mass on a spring, okay, because it's easier to see it there, okay, here the object is at its equilibrium position at rest, okay? Then it's pulled away from equilibrium. In order to do that, you have to do work, okay? Would you have a force and a distance there? So you'd be able to calculate how much work, agree? Now, when we're at this position, okay, our acceleration is at its maximum because the force used would also be at its maximum. I would have to pull really hard to move it that far away. Okay? So when you are at your maximum amplitude, you have the greatest acceleration, the greatest force, and the greatest amount of potential energy. Right? Do you have any kinetic energy at that position? Why don't you? Okay, picture it oscillating back and forth. When it gets to its maximum amplitude, how fast is it going? Right? As it moves through equilibrium, okay, so if I pulled it out to here and I let it go, it's going to snap back to equilibrium because the spring is going to pull it back. But once it passes equilibrium, it starts to compress the spring. Is the spring going to push back? Is that going to slow it down? Eventually, it's going to stop. Okay? That's why at that maximum amplitude, the speed is 0, and thus the kinetic energy is also 0. All right. As this thing moves back to equilibrium, does its speed increase? Okay. Would its maximum speed occur at equilibrium then? Because once it passes equilibrium, the spring is going to start to slow it down again. Right? Either way. So here, its acceleration is 0, but its speed is its maximum. Why is the acceleration 0 here? What is the spring not doing at equilibrium? Okay, it's not accelerating because the spring's not doing something. What's the spring not doing at equilibrium? It's not doing any work because it's not exerting any force. Okay? Equilibrium is where the spring is neither stretched nor is it compressed. That's where it would sit if you didn't disturb it. So at that position, it doesn't exert any force. So there's no acceleration, no force, and no potential energy. But there's lots of what kind of energy? Kinetic, yeah. Okay, because your speed is at its maximum, right? Okay? At equilibrium, that's where it's going the fastest. So all of the potential energy that you had here is now kinetic here. And as you move away, that kinetic will go away, do work on the spring, and turn it back into potential energy. That's why simple harmonic motion can occur. You're just conserving energy. Just like we did with the roller coaster questions, instead of gravitational potential energy, now we're going to be dealing with elastic potential energy. It works exactly the same, okay? It's just a different kind of potential energy. All right, so we pass through equilibrium, okay, we move to here, spring gets compressed, exerts the most force, produces the most acceleration, but the object stops for an instant before it goes back to its equilibrium position. Okay? Everybody all right with the path a mass on a spring would follow? Okay, so the amount of time that it takes to do this would be the period. Yeah, would be the period of the oscillation. Okay. What shape did that produce? A wave. Remember how I said simple harmonic motion and waves go together? If something is oscillating with simple harmonic motion, it can produce a wave. That's why we get a wave when we do that. Okay, so if I'm talking about a mass and a spring, what two things do you suppose would affect the period of this system? Assuming it's horizontal. Yes, but the speed is influenced by the two things I'm thinking of. So yeah, you're absolutely right, yeah. It's a mass on a spring. What two things would affect it?
Well, how far you like originally pull it back, or like push it in?
Believe it or not, it doesn't. Strange, but true. Okay, it seems like that should, but remember, the further I go, the harder it pushes. So I get actually more acceleration. So it actually takes the same amount of, we're actually going to do a lab with a pendulum where I'll prove it to you, or you'll prove it to yourself. Okay, that it doesn't matter how far from equilibrium you take it, it takes the same amount of time to complete a cycle, because it'll go faster, right?
Is the strength of the spring and the amount of mass?
Exactly. It's a mass on the spring. The two things that can affect it are the mass and the spring. Are all springs the same? Right? You wouldn't take a spring from your car and put it inside a clicker pen. Okay? You'd never be able to click the pen, and it would be really heavy and awkward. Okay? Those two springs are very different. Okay? If I put 1 kilogram worth of mass on the spring from a clicker pen, okay, and then let it go, it would destroy the spring, right? It doesn't have enough strength in it to take that. If I put that same mass on the spring from a car, it would hardly make it move at all. Would that affect then how long it takes to make a full cycle? Right? On a small spring, a lot of mass is going to really stretch that spring, and the period is going to be very large. On a small spring, it's going to oscillate up and down just a tiny bit and take no time at all to complete a cycle. So the two things that can affect how long it takes a mass on a spring to oscillate are the mass and the spring. It was a trick question. So that probably seemed like that was too easy to be the right answer. All right, so this formula is on your formula sheet. Okay, this is how you calculate the period of a mass on a spring. Okay, so you take 2 pi and you multiply it by the square root of the mass divided by the spring's constant. Okay? The spring constant is how stiff the spring is. Okay? We measure spring constant in newtons per meter. Okay, so K is the stiffness of the spring, okay, which we also call spring constant. Okay, and that is in newtons per meter. Okay, if I want to solve for anything other than period with that formula, what am I going to have to do with everything in that formula? Square it. Yeah, I'll have to get rid of the roots. Okay, so I'd have to square everything if I wanted to solve for m or k. All right. Everybody all right with that formula? Okay, and you'll never set that equal to anything else. That formula is to calculate the period of a mass on a spring. All right, so let's say we've got this example here. We put a ball that has a mass of 0.2 kilograms on a vertical spring, okay, that has a tension or spring constant of 28 newtons per meter. Okay, the ball is released. How long does it take for the ball to complete one complete oscillation? All right, so we're looking for period. We have mass. We have spring constant. All right, it means we don't have to manipulate the formula. Okay, we're just plugging in our numbers here. Okay, as I said, not a hard formula to use. Okay, we're going to have 2 times pi times the square root of m over k is So that'll be 2 pi times the square root of 0.2 kilograms divided by 28 newtons per meter. All right, gonna take just over half a second to complete an oscillation. Okay, everybody all right with that idea of period and mass and spring constant? Okay. So pendulum, also an example of an object oscillating with simple harmonic motion. What two things would affect how long it takes the pendulum to oscillate back and forth? And it is only two things.
I don't know mass is one, but I don't know the length of the strings.
Length of the string is definitely one, right? Like when it's this long, it oscillates back and forth really fast. When I'm using the full length, it takes a lot longer to go back and forth. Length is definitely one. Mass is the most common answer I get first, but it's not true because all masses fall at the same rate. So it doesn't matter whether I've got a roll of tape on here or a garbage truck. Well, Roots wouldn't support that, but okay, it would swing at the same rate because all things accelerate at 9.81. Could that be the other thing? Right? If I did this on the moon, would it look like this? No, it would look like this. It would be a lot slower. Okay? Because on the moon, the acceleration due to gravity is only 1.6 meters per second squared. Okay? They actually did some of this stuff when they were on the moon. Okay? It helped them to confirm little details like the radius of the moon and mass of the moon and things like that. Okay? Everybody with me on those ideas? Okay, so if we're talking about a pendulum, okay, the two things that affect the period of a pendulum are the length of the pendulum and the acceleration due to gravity. Okay, so the formula looks very similar, it's just got L and G in it instead of M and K. What's the name for the mass on the end of a pendulum? Anyone know what the name of the mass on the end of a pendulum is? Bob. I kid you not. Okay, the mass, the name we give the mass on the end of a pendulum is Bob. It's the pendulum bob. Okay, so I don't know why that is, but okay. Well, in case you get a question that goes, the bob of a pendulum has this mass, but this is Bob. Okay, Bob is the thing at the end of the pendulum. Okay, so I don't know who came up with that, but it's someone who wanted to spell their name forwards and backwards the same way. True story. Yeah. All right, so if we want to use this formula to calculate the period of a pendulum located somewhere where gravity is 9.71 meters per second squared, we just plug the numbers into the formula. T equals 2 pi times the square root of L, in this case 1.5 or 1.55 meters, divided by the acceleration due to gravity, and we would find that that pendulum would take 2.51 seconds to complete an oscillation. Okay? They're pretty easy formulas to use, and again, if you need to manipulate them, you first have to square everything. Okay? All right, so the bottom of the pendulum is pendulum bob, plumb bob, square pants. Okay? He lives in a pineapple under the sea. Absorbent and porous and yellow is he. You're welcome, you're going to have that in your head now all day. That was so cruel, but I did it. I'm sorry. Okay. By the way, don't watch that show. Apparently you get dumber by watching it. Okay? Apparently somebody did a study where they actually found you get dumber from watching SpongeBob. So don't watch SpongeBob. All right. I want you guys to try this one. Determine the length of a pendulum that swings back and forth with a period of exactly 1 second on Earth, where gravity is 9.81 meters per second squared. Okay, so this question gives us the period, tells us it's 1.00 seconds, gives us acceleration due to gravity at 9.81 meters per second squared, right? We know we're using this formula. T equals 2 pi times the square root of L over G. So as we were saying before, if I want to solve for anything other than period, I've got to square everything. So T squared equals 4 pi squared times L over G. Right, now that I've squared everything, now I can start moving things around. Okay, so I multiply both sides by G, divide both sides by 4 pi squared. That's going to leave me with L, and then I just have to plug in my numbers. 1 squared is 1, okay, so times 9.81, so I just got 9.81 on the top, okay, divided by 4 pi squared. Okay, so that pendulum would be about 25 centimeters long. Okay, everybody all right with how that formula works? Okay, it's nothing too complex. All right. On an exam or a quiz about simple harmonic motion, okay, you're just going to get problems to solve like this. Nothing terribly complex. You could get some multiple choice questions that ask you about your understanding of simple harmonic motion. Included in questions like that would be things like, what's the force called that makes a pendulum go back and forth? And the answer would be restoring force. Okay, that restoring force needs to do what as it gets further from equilibrium? Somebody whispered it. It needs to increase linearly, right? Okay, restoring force must vary linearly with displacement. So the further from equilibrium you get, it has to go up. Okay, so whatever force you used at 1 centimeter, you're going to use twice as much at 2, and 3 times as much at 3, okay, and so on and so on. All right, so little things like that, okay, those are more understanding kind of things. You just got to go through your notes, okay, when you're studying for that kind of stuff. All right. Okay, see if you can solve for what G would be on a planet where a 0.65 meter long pendulum has a period of 2.8 seconds. Okay, so on this one, okay, our givens are, we know the length, 0.65 meters. We know the period, 2.8 seconds. Right? T equals 2 pi root L over G. Okay, I'm trying to solve for G, so I've got to square everything. T squared, 4 pi squared times L over G, and then we're just going to cross multiply our T squared and G. So G will equal 4 pi squared times L over T squared. What do you suppose people forget with this manipulation? They forget the square period, yeah, like all the time. I'm not sure why, but it happens, okay, a lot. So we got 4 pi squared times 0.65 meters, okay, divided by 2.8 squared. Okay, so the acceleration due to gravity on that planet is 3.27 meters per second squared, which means it's probably Mars, where the gravity is 1/3 of Earth. That is almost exactly 1/3 of 9.81. Okay. All right, how are we feeling about this stuff? Okay, good news is this stuff is probably some of the easiest stuff in the whole course. Okay? And there's quite a bit of that in Unit 4 as well. Okay, we haven't talked about this for a while. This question gives you the period of something and wants you to find the frequency. How do you do that? Yeah, T is 1 over F. So F is 1 over T. Okay? That formula comes up a lot more in Unit 4 than it did in the circular motion unit. So just be aware, that's a formula you're probably going to use quite a bit in this course. Okay? So if that's the frequency, okay, then we would go 1 divided by 0.0625. Right? That means it's oscillating at 16 hertz. Okay? Or it's going up and down 16 times per second. Everybody all right with that? Yeah? No, we haven't done enough to do that one yet. More of those. Okay, that one we can do. I want you to try and calculate the gravitational field strength, which is also known as acceleration due to gravity, okay, at the top of Mount Everest, okay, that has that altitude, if a pendulum with a length of 1 meter has a period of 2.01 seconds. Okay, so for this one here, okay, we're told the mass that's on the spring, so 0.50 kilograms. Okay, we're told that the spring constant is 82 newtons per meter, so we are given K there, right? We're looking for T, so we don't have to manipulate. T equals 2 pi times the square root of M divided by K. All right, so just plug in our numbers here. 2 pi times the square root of 0.5 divided by 82. Okay, so we should get 0.49 seconds. Okay, everybody all right with that? Okay, again, the good news here, guys, is you're never going to set these formulas equal to anything else. Okay, one of them calculates the period of a pendulum, one of them calculates the period of a mass on a spring, and that's all they're ever used for. Okay, I'm going to put up the worksheet on this stuff here for you guys to, actually, you know what? I need to photocopy it. Okay, I'm going to give you guys, but I'll hole punch it first. So this sheet, you're going to need to hang on to it because we'll be working on some of the questions on it on Friday and Monday. Okay, so don't lose it. Okay, first side is all what we're working on today. Okay, so simple harmonic motion worksheet, that's on these two formulas and these two formulas only. Yep. All right, any of those give us trouble, and we'll go through them together, guys, just ask. Okay, so we have an 8.8 Newton object. What did they give me there? They gave me the weight. What do I need? Mass. Okay, so first thing I got to do is get mass. So I'm going to go force of gravity over G, right? Because I'm just using this formula, F G equals M times G. I'm just solving for M. So 8.8 divided by 9.81 will give me the mass. All right, so we're looking at 0.897 kilograms. I'll keep all the decimals in my calculator for that. Okay, vibrates along a horizontal spring on a frictionless surface. The period is 1.1 seconds. All right, so I've got the mass, I've got the period. Okay, T equals 2 pi root m over k, and I am trying to find the spring constant. So I'm looking for k. So I've got to square everything. T squared 4 pi squared times m over k, and then I'm just going to switch t squared and k, right, to get k by itself. So k will equal 4 pi squared times 0.897 divided by 1.1 squared. Right, when we do that, we should end up with 29 newtons per meter. Okay, dirty trick in that one, giving you the weight instead of the mass. Okay, any other ones? Okay, keep going then. Okay, guys, let's have a quick look at, maximum displacement is, yeah, you can't do that one. Because I haven't taught you Hooke's Law and conservation of energy yet. That is what I'm going to teach you on Thursday and Friday, because we said this week there won't be a quiz. Okay, so I can understand your dilemma, predicament with number 8. It's, yeah, you can't do number 8 because I haven't taught you that stuff yet. Yeah. So don't worry about that one. It's about Hooke's Law. We haven't done that yet. Okay. Are the other ones like that? No, the other ones are. No, the other ones you can do. That one's off. Yeah, that one actually is supposed to be on the other worksheet. Okay, so this one here is just about period and frequency. So the spring vibrates 32 times in 56 seconds. Okay, so here's what we have to remember, and that's all this question is testing is, do you remember that period is seconds per cycle and frequency is cycles per second? Okay, so to get period, I'm going to go 56 divided by 32. Okay, because that's going to be seconds divided by cycles. Right, and so I'll get seconds per cycle, 1.8 seconds. If I want to know how many cycles per second, then I'll go 32 divided by 56, or go 1 over that number. Either way will work. Okay, so all it's doing is just trying to remind you, hey, remember that period is the seconds per cycle and frequency is the cycles per second. Okay, that's really all that one is checking. But it's not something we've done a lot of, so okay, it's valuable to have that. 11? Okay, length of a pendulum that has a period of 2 seconds. We're assuming this is on Earth at 9.81. Okay, so period equals 2 pi root L over G. Okay, square everything. T squared equals 4 pi squared L over G. And we're looking for L, so we multiply both sides by G, divide both sides by 4 pi squared. Okay, that should leave us with L. So 2 squared times 9.81 divided by 4 pi squared. Okay, so 4 times 9.81, okay, divided by 4 pi squared. 0.99. Did you bracket top and bottom? Did you bracket top and bottom? Yeah. Or you forget to square something somewhere in there, yeah. Okay, so remember, if you want to start early tomorrow on your exam, you can do that. Show up at 12:05. I'll let you have your test once your phone's in the pocket and everything. And then, like I say, Thursday we'll go over the test and keep going on simple harmonic motion. Then you'll be able to do questions like number 8. Okay, and then next week, okay, I'll probably hopefully get into waves next week and doing a lab on pendulums. And hopefully on Monday we'll be doing a lab on pendulums. Or pendula. What would it be? What would the plural be? Pendulums or pendula? Pendulums. Like octopus is octopi. Should pendulum be pendulum?
I'm sure that, no, I think.
Pendulums, okay. I'll go with that.
Yeah, I usually tend to put in vowel and an S.
Yeah.
S so it's not vowel S.
Makes sense. English is a weird language. So.
Yeah, I'm not an expert at it, so I don't know.
I was very concerned that not even asking.
Why aren't many moose called geese? If lots of gooses are called geese, why aren't lots of gooses called geese?
That makes it very
Yeah, pendulum. Okay. Google says so.
Yeah.